Okay, so these are some of the commonly missed problems for a cart on a ramp. Some of the most commonly missed things that students said was that there was a friction force. Well, there is a rolling friction force, but we have not studied that. We have no idea about that. There definitely is not a sliding friction force, and there's not a static friction force on this. So there's no friction in those cases with wheels. Another commonly missed thing that students do is they're still saying that inertia is a force. In other words, when they're thinking of the force diagram, they end up having a force that's usually in the direction of the motion. And I think if you just simply figured out what the dealers were, feeler-dealer notation, you would see that there is no such force there. The first number of the code is 7. One of the problems often missed on the Swyk constant net force Swyk 3 was problems like this where there's multiple objects being pulled. So you need to understand that you're in charge of making your system whatever it is. So notice in this problem, we know what this tension T1 is. And so maybe we're asked to find the acceleration, maybe we're asked to find T2 or the F. But I would suggest drawing a force diagram sort of like this. Sorry about that. Sort of like this. There we go. Because we know what T1 is, and so now if you draw the force diagram for both objects A and B combined, you don't even have to worry about T2. You could then figure out what the acceleration is. Maybe that's the answer. And then, or maybe it's not the answer. Maybe they want you to know what T2 is. Well, then draw another force diagram. You now know what the acceleration is, solve for T2. Or maybe we want to find this force. So draw another force diagram. You know what the acceleration is now, and solve for the force. So that's how I would go about solving this problem. The next number in the code is 4. This is another often missed problem. So, so this one's asking us to find the tension, but it could ask us to find what the acceleration is, or it could ask us to solve for what the friction is, or whatever. I would advise making one system. So something like this. The next number in the code is 4. And if I draw the force diagram for just the entire system, weight B is causing the thing to speed up, and the only thing opposing weight B is the friction, Fk. And so the net force would be the weight B minus the friction. The inertia of the system, I could find the total inertia, it'd be 28. And then I could solve for the acceleration. Or if they give me the acceleration, I could solve for the friction. If they're asking for something different, let's say they're asking for the tension, like in this problem, I would just simply draw a force diagram for B, because it only has 2 forces on it, and there would be a weight force down and tension force up, and they happen to give us the acceleration here. But even if they didn't tell us the acceleration, we could solve the acceleration from the earlier part, and then we can go ahead and figure out what that tension would be. Okay. Here's another often missed problem. The next number is 3 in the code. And so it could ask us lots of different things, like what's the acceleration, or maybe it'll ask us what the tension, T1 or T2 is. I would choose my entire system here, everything in my system, and figure out what's causing it to accelerate. Well, the weight of A causes it to accelerate, and so does the weight of B cause it to accelerate. And what opposes it? The weight of C. So something like that. From that, I can figure out what my acceleration is, because the net force would be weight A plus weight B minus weight C, divided by the entire system inertia mass, and I can find the acceleration. Maybe that's my answer. Maybe it's asking for tension 1. If it's asking for tension 1, then I would probably draw another force diagram for just object A, maybe. And so it'd have a weight down that's bigger than the tension up. And I just found out what the acceleration is, so I can write a net force equation and solve for tension 1. Perhaps it's asking for tension 2 and not tension 1. I think I would make C my system. And so in that case, I'd have tension 2 up, that's bigger than weight C down. I already found the acceleration as explained earlier. And then I can find out what the tension is by writing a net force equation. F net equals T2 minus weight C. Okay, here's another often missed problem. And so in this one, we're trying to figure out how much friction, but maybe they might ask us what the acceleration is, or maybe they might ask us the tension on the left or the tension on the right. All those types of problems, all those different variations we can solve. The next number in the code is 9. And so I'm going to treat this whole thing as my system. Weight A is the one that's causing it to accelerate, and what's opposing it? Well, there would be a weight C that opposes it, and if there's any friction, and it looks like there is in this case, the friction on B opposes it. So then I can write a net force equation. F net would be equal to WA minus WC minus FK, and then I can use the idea that A equals F net over M, and either solve for the acceleration, or in this case, for instance, they give us the acceleration, so then I could solve for how much friction there is. Let's say they didn't tell us what the acceleration is, and then we can go ahead and solve for the acceleration. And after we find the acceleration, maybe we're asked to find the tension on the left-hand side. So I think I'd draw a force diagram for object A. There would be a weight A down, which is bigger than the tension up. I just found the acceleration, and then I can solve for the tension. Or maybe we're asked for the tension on the right-hand side. So there would be a bigger tension force up than the weight C downward. Write another net force equation, plug in the acceleration, and solve it. Here's another one that students had a hard time with. So again, this one's asking for, well, I don't know exactly what it's asking for, but it could ask for the acceleration. It could ask how much friction there is. It could ask us what the tension force is. So for this, I would say that there's a weight B that opposes a weight A and also maybe a friction force. So kind of like, actually it's the A, the X component of A, not all of the weight of A. And so again, I can write a net force equation. That would be WB minus WAX minus the friction. And that divided by the entire system mass would give me the acceleration. Now, if I know the acceleration, I could figure out what the friction is. Or maybe it's asking us for the tension. Well, then I would probably choose my object B as my system. I have a weight B that's downward, and it's larger than the tension that's up. And so I'd write a net force equation, and then I could plug in the acceleration and solve for the tension. And here's one more that students had a hard time with. The last number in the code is 2. And so this could ask us what the acceleration is, or it could ask us what the tension is in the string. It could ask us any of those things. So again, I would choose one object, or choose one system to solve this. And I think I would, let's see, looking at the masses, I think A is going to cause it to accelerate, and B is the one that opposes it. Again, it's only the X component, sorry. The X component of A is opposing the X component of B. And so I could write my net force equation and plug in, where is it at? Here, sorry. That would be WAX minus WPX. That would be my net force divided by the entire system's mass, and I could find the acceleration. Or if they give us the acceleration, we could choose object B to be the system, and so I could write a net force equation for that, and that would be a tension force minus WBX would be equal to the F net I just found the acceleration, and so I could plug in and solve for the tension force.